Hello, I'm Keith Oakley and welcome to my second talk on quiet hovercraft, the recipe, how to make them quieter. This one is a summary of the question and answer session that we had a couple of days after the first talk went out. We had a series of questions coming in from all over the world by email and on the interactive Zoom Q&A session. And what I've tried to do in this little presentation is to pull together both the questions that were asked, my answers, and to try and reflect everybody's point of view a bit. There were a lot of questions about the splitter on my integrated craft Q1. And one of the best ways of showing you that is the work that I've currently got in progress at the moment in my garage to convert a 35-year-old Osprey 3 into a quiet craft. You'll see there are two different colors of yellow. The older, darker yellow is the original hull. The lighter yellow is the new moldings that we've made to drop into that craft. And essentially it will fit a thrust unit and a lift unit, integrated unit, that is very similar to the one that was developed on Q1. You can see there the engine. In this case, it's an uprated engine. It's a 50 horsepower version of the Briggs & Stratton engine. Same fan, however, slightly up pitched. It's a rear drive setup. These shafts at the top here, I'm showing with a cursor, they're only a temporary aluminium tubes in for alignment of things. And so that won't be there in the final animal. You will, however, have a proper drive shaft here with universal coupling, which will drive down to the back of the craft to a small pulley down here underneath that coaming, and then up with a 50mm tooth belt to a larger pulley at the top. In my case, it's a 34 tooth down there and an 80 tooth up here. And then the shaft there comes forward and mounts this multi-ring 1W fan, as you can see. You can see the splitter set up there. There's an A-shaped splitter. There's one side. There's the other side. There's the vertical splitter. And you can see the shaping of the ductwork, if you like, that tries to lead the air away from the fan into the side bodies as smoothly as possible. Now, because this craft is only in pieces at the moment, literally I've made a lot of sections and I've just put them together just to test how they fit and to show you how the thing's put together. So I've taken off the top duct and you're now looking at the splitter assembly. That's the top cover of the splitter assembly. There's an inspection hatch there which is missing at the moment, taken out. And as you can see, the pieces are only slightly put in rather loosely because there's a bit of a gap there which shouldn't be there. You can see there the 70mm gap between the trailing edge of the fan and the leading edge of the splitter. You can see also how the splitter is shaped to reflect the curve of the fan. I've taken that cover off, and in this shot, looking downwards, you can see the inner cover, the undercover, if you like. And here I've picked out in green the shape of the splitter. The fan is basically swirling around, trying to push air down the right-hand side. So that vertical splitter there is catching this air, which would normally, in most integrated craft, be shoved down the right-hand side of the craft. It's catching it here and turning it and taking it down the left. And then the other half is going in the normal fashion around to the right. So that's the profile, if you like, of the vertical splitter that's splitting left from right. Now, as I've said in the previous presentation, I prefer an A-shaped splitter. And I try to explain in this little slide here why that is. When we were doing testing with Keith Smallwood in Vortex about 10 years ago now, we discovered that there was an issue with a flat plate splitter, which perhaps hadn't come up before. And that is as the, let's take this blade here, it's rotating around. At this point in time, the blade is above what I call the horizon of the flat splitter plate here. So that area is going to be blowing, it's going to be high pressure behind the fan. However, this area is not yet above the horizon, so in comparative terms, it's going to be low pressure. Air will normally go from high to low, so that's what happens. The air, a lot of it is going backwards, absolutely agreed, pushing the craft along, but some of it is flowing sideways in a kind of span-wise flow across the splitter from high to low. And if I look over the other side of the blade fan at the moment, you've got the opposite situation where it's high at the tip because this piece is still above the horizon. It's low here, the blade hasn't arrived yet, so you're going to get a flow that way. And of course, as the blade passes the splitter, you're going to get a reversal of that. High will go to low and so on. So you've got a circulating eddy. And those circulating eddies are happening every time a blade goes by. That's a bang every time a blade goes by. And that's one of the major noise sources that we hear. Excuse me. With the A-shaped splitter shown in green here, and I've left out the vertical splitter for simplicity in this diagram. With the A-shaped splitter, the blade crosses the horizon at about the same time, uniformly along the splitter. So you don't get these cross-flow eddies, and therefore one noise source of many is eliminated. Don't forget, you also need to shape the blade so that they point in towards the swirl of air. The leading edge of the blade still needs to be shaped, as perhaps you saw in the earlier diagram of the real thing. Splitter gate plate gap. Somebody asked me about, if you like, the science behind the splitter plate gap. Well, we did test 4 different splitter plates, which we could drop in and out of the test craft Q1 and give us different distances between the trailing edge of the fan and the leading edge of the splitter. And what we got was, fairly obviously, the bigger the gap, the less noise, because there was less interaction between the two items, but the poorer was the lift. Out of that, I came up with a compromise where I basically say I recommend that you have a gap above 50 millimeter. And Q1 and now this new craft, we're using 70 millimeters. Just to give you an example, the difference between 50 and 70 millimeters on my test craft was around about 1 dB. So it made it about 1 dB quieter to go from 50 to 70. Clearly you could make it 100 or much more, but your lift is going down and there's not quite so much gain on the noise front. So 70 is about the compromise that I feel works. And again, I make this point, assuming the splitter is angled to meet the swirl's airflow. Just to mention that to define poorer lift, I mean, we all know what poorer lift is. It's when the craft feels floppy and soggy. But I had to put a number to that for this test. I could obviously measure the dB accurately, but what was the number for poorer lift? And I defined it as the minimum engine RPM that a correctly trimmed craft just lifts on flat tarmac. So you put on a flat surface, smooth surface, not grass. You trim the craft with nobody in it, the way we did it, so that when the craft does lift off, it's level. It's not tipping down at the back or the front. And then we slowly, very slowly, leant into the craft, slowly worked the throttle until it just lifts to the point where you could push it. It wasn't, the skids weren't scraping across the tarmac. And that we defined as our just lift point, just to get a measure of lift performance. Just as an example, I think the tighter gap, that 1700 RPM was at 70 mil, I think. If you went down to a tighter gap, it went down to about 1500 RPM or something like that. So it made a small difference. At the other extreme, we did try leaving the splitter out completely, which meant that the back wall of the splitter assembly was really the agent that pushed the air downwards. As you can imagine, the lift was as soggy as old boot, but it did lift at about 2,800 RPM. You wouldn't have wanted to drive it like that. So it's quite about getting the right compromise. Now, how do I feed the air to the rear segments was a question that came up in the Q&A section. I've gone back to that diagram that you saw earlier, which shows in white now, I've picked them out in white, these feed holes at the bottom and top of the planing surface there, which are feeding air into the individual rear segments. Now, obviously, this box here, this triangular shaped box, on my craft is a sealed box. There's no air naturally going into it, which is good because the drive stays nice and clean, and if the belt comes off, it just stays there in the box. But there is the issue of feeding these segments. Now, it is a point that this design here was borrowed from Owen Ellis's work, but with a subtle difference. Owen actually has a gap here where I've marked it in red, and there's a small slot, let's say, between these two faces, which does allow in, and he uses that air to pressurize these rear segments. Now, I was worried that this might possibly be a noise source, a bit like blowing over the top of a bottle. So I decided not to do that, and to go for an alternative approach. Now, I would stress might. I've not had a good chance to test Owen's design of craft, so I can't say hand on heart, yes, it is a noise source that's significant. It's only, if you like, a concern. So I decided not to go down that road. So I had a problem of how do I find air to feed these 4 or 5 segments in the center here. And the solution I used on Q1, and I'll use again on this new craft, is to make a small hole, about 3-inch diameter here and another one here, and use that to feed air into a very small plenum chamber, a small tube, if you like, which feeds air to the back. That works perfectly well on Q1, no issues with soggy rear segments or anything like that. Right, one of the topics that came up very strongly in the discussion was the whole issue about how you made the duct structure. What you're trying to achieve, of course, is you're trying to achieve a minimum and uniform fan tip clearance, because from a noise perspective, that's going to make it quiet. It's also going to make crafting more efficient. But there's also a point, if you can make a really solid, strong structure here that locks the fan to the duct, so the fan can't move around relative to the duct, and the fan tip hit the duct, then that's very much reduced the risk of fan damage. And it's felt in operational experience that the vast majority of fan damage has been caused by some kind of shock loading, moving the fan relative to the duct, the fan impacting the duct at quite a high speed, and damage occurring. So the approach that Owen took, and I followed really, is to make the splitter and the flow straighteners, which support the fan, i.e. they mount the hub of the fan, the shaft there, make those struts part of an integral duct module. They're really solid. They brace the center fan hub to the duct on the outside. And then the second thing that I've done is to join the inner and outer duct moldings with radial ribs. So here you see in red 2 radial ribs. They very much stiffen this outer wall of the duct here so that it can't flex. And they make this whole structure into a series of monocoque boxes by locking the inner and outer units together. And of course, monocoque is the way most modern cars are built, and it's definitely the way forward. It's the light way forward. One thing I don't think I want you to do is to use rubber mountings between the fan duct, between the fan frame and the duct, and there's a lot of craft like that. If you use rubber mountings, you're basically saying the fan can move around relative to the duct. Okay, it doesn't impact the duct, but one day on a shock loading it will, and that could be a cause of failure. Now, a topic that actually formed part of a key part of my research, but I forgot to mention it in the original talk, and Pascal Lepissier pointed it out to me in a beautiful slide that he drew, which is that the hull structure itself can be a source of noise. There are very many hulls which are thin plastic, thin single layer, say GLP or plywood, as this craft I think is, where the hull will resonate, it will vibrate. You put your hand on the side of quite a lot of craft and you can feel the side bodies drumming up and down. They're big big loudspeakers in effect. Now, Q1 just happens to be foam sandwich. It was made 20 years ago as an experimenting foam sandwich. It's extremely stiff, and it as a structure, it's very much lighter. And of course, it's got foam built into it, so it's self-buoyant. And it's incredibly strong. I mean, we've had 4 people, full-grown adults, sit on the side of Q1 formed, and nothing deflects at all. Where you wouldn't do that really in probably a child on a lot of craft. So I really strongly recommend foam sandwich or some structure like that gives you a stiffer but also lighter and self-buoyant hull. This is the structure of Q1 thereabouts, given my poor drawing skills. Basically, it's a 10mm thick foam. It's actually something called Tricast 6. You'll find it on the internet. With either side of it, 1 layer of 200-gram cloth and epoxy resin. I mean, I would think the skinning, if you like, that cloth is perhaps 1 millimeter thick or something less than that. The planing surface on my craft is a foam very similar to Tricast 2, again with 1 layer of cloth either side of it, but it's Tricast 2 foam, which is less dense, and it's a lot thicker to give a buoyancy slab. By putting it there, it's obviously part of the structure, but it's also putting the reserve emergency buoyancy where you want it if your craft's going to get flooded. Bottom, same structure, but beefed up with Kevlar on the bottom and also on the floor of the craft. I found from experience it was quite easy to put my feet through that over a period of time. So thanks to Pascal for this picture, particularly the drum at the top. And I'd also point to the fact that he gave me this original sketch as part of a series of slides. He's converted my slides into French, which I think is absolutely brilliant. So if any of you would find that more convenient to watch the original talk in French, or at least the slides in French, then there's a link you can use there to go to his website, where there's a lot of other useful information as well. So on to twin engine craft. It was pointed out that a lot of my talk originally focused in on integrated craft. There were 2 reasons for that. First of all, integrated craft are a compromise between lift and thrust. So it is more, and you've got the inherent noise of the splitter. So it is inherently more difficult to make them quieter. But also, the 2 companies I was working with, Vortex and Flying Fish, both at the time wanted to produce quieter versions of their existing integrated craft. So there was a focus on that. Plus, of course, I had a spare integrated craft lying around in the garden to use as a test bed. So that's why the focus was on integrated. But actually, of course, over the years, I've tested as many, probably more, twin engine craft, racing and cruising, with noise cam, and there's a lot of data on those. So, as I say, an integrated craft is always going to be that fan and the setup is always going to be a compromise between the lift and the thrust, especially on a cruiser, where you want it perhaps to lift off at quite low revs, so that you're going along quite slowly. A twin engine craft should be more efficient. You can optimize each of the fans to be efficient for the sort of thing you're using it for, a thrust fan or propeller, or a lift fan, and possibly even a centrifugal lift fan, which, if you can get them, are quite efficient and quiet. So a twin should be more efficient and therefore potentially quieter. Efficiency, particularly for a cruiser, equals quietness, because it means you can jog along at 10, 15, 20 knots on something under half power probably. if your craft is efficient. If you're straining to get airborne at all and giving it full welly just to make that kind of speed, it's not necessarily going to be quiet. But twin engine craft, 3-engine craft, as I had in my early career, you've got 2 sources to silence, 2 sets of fans, 2 sets of engines to silence. Usually the thrust is the noisier engine, simply because there's more horsepower involved, particularly on a racing craft. There's a lot more horsepower involved in that. But often I find the lift is noisier than it needs to be. The lift could be very quiet, but people make mistakes, if you like, in the way the lift is put together, and that makes it noisier than it might be. So I've picked out a few of the slides that came from my worldwide study, showing some lift engine noise. This happens to be 909. It's an Italian craft, and actually it's got something I'd recommend, which is the engine is not driving the fan directly. It's driving it via a belt. Quite a lot of the problems come from the fact that the engine is directly coupled to the fan. The fan is therefore running quite fast, even though it's small. The tip speed is comparatively high and therefore noisy. But here it is decoupled with a belt, and so it's running at a lower speed. But in this case, you can see that NoiseCam showed a fairly classic. Our highest noise was from the air intake, from that classic foam silencer there. Again, that could have had something of an airbox around that. That would have silenced that quite a lot. And then the second largest engine noise is the exhaust outlet. Well, there's a big tuning system there. That's the only real silencer. And it's better than many I've seen. The worst cases are when there's a small box silencer directly connected to the engine. And they're usually pretty noisy. But a more efficient silencer might make that noise a bit less. Lift fan noise. It's often the case that a lift fan and engine are squeezed into quite a tiny space. And that means things are close together, and that means things are noisy. In this particular case, this German craft, I picked up a noise source, which was the fan blade rotating frequency. And it was occurring here, basically just below the bowl of the lift fan, of the carburetor, because the bowl of the carburetor was very close to the fan, causing turbulence every time the blade went past. I can't remember exactly what it was, but of the order of an inch, 25 millimeters, something like that. So the message here is, it's the same message. Keep everything, the struts, the bowls of carburetors, the head of the engine, etc., away from the fan as far as you can. Of course, you know, there's structural problems in the space available to achieve that. Excuse me. The thrust, that's challenging, particularly on racing craft, because you've got lots and lots of high-powered sources of noise. And you know, we said right from the beginning that the more horsepower you've got, the more noise you're intrinsically going to make. And the real challenge is not that we don't know what to do to silence the noise. We know where the sources are, but how do you engineer this high-powered machine so that it is safe and viable when racing around, but also achieves the kind of separations you need between the engine and fan and structure and fan, etc., to get the noise down. Let's take this one just as an example. It's simply one I had a slide on. Again, it's a Dutch craft. All the figures quoted here are relative to the loudest source, which in this case was the exhaust. So that exhaust was the loudest. Again, it looks a pretty impressive silencer, but it's a sport silencer. It's probably not necessarily the quietest one that you could have got for that motorbike engine. There's another leak here. There's another source here, which is about 6 dB below the exhaust noise. But that noise seemed to be from a leaking manifold, a joint in the pipework. And that's not uncommon. There was a famous American craft, which will remain nameless, where I pointed to a noise source apparently on the side of the engine. And neither myself or the owner could see a hole. but I put my hand around the back of the manifold and it came away covered in black soot. There was clearly a hole, but it was hidden from view around the back. And that's not uncommon, that I find really faults that are not necessarily apparent to the eye. And those are obviously, you know, fairly straightforward to deal with. Some of the other noise sources on this craft, classic pulley, extremely in a cutout, extremely close to the fan, big source of noise, in this case about 2 dBs less than the engine noise. Fan noise itself from the struts up here, both at the blade passing frequency F and at the 2F, the second harmonic, the fan frequency times 2. And the higher the harmonic, the more higher the frequency, the more shrill it's going to be. So the challenge really with twin engine high powered craft is not, do we know what makes the noise? Yes, we do. The challenge is to engineer it so that it's still a viable racing craft. And we're never going to get those sort of craft down to the low 70s that I'm looking for cruisers, but it would be quite nice if we could get a number of the racing craft down to the 96 dB official limit. A lot of them are in excess of that. Excuse me. Furious discussion occurred after the Q&A session by email across 4 continents with Owen Ellis in Montreal, Paul Moody in Australia, Paul Hibbard in Singapore, and myself in sunny Kent, UK, about does pre-swirl exist? If you remember, I said that we all know that there is swirl of the air behind the fan, but to some extent, I believe there can be swirl very close to the front of the fan as the air is picked up by the blade and started to spin before it happens. Now, Owen sent me some nice videos indeed of some string tests he'd done a few years ago on one of his craft. And I've picked it, you couldn't see the original black strings very easily. So I've picked them out in red, and hopefully I've faithfully shown you where they are. And as you can see, that's showing that the air is going in at the duct edge there to the fan extremely straight and clean. There are no apparent swirl there. But down here, I showed you in the earlier presentation, the Griffin craft, where the pylon there is clearly producing a turbulent air behind the pylon as it hits the fan. That noise source there is clearly at an angle. It's not vertical. And that suggests that the fan, which is going around like that, the air is swirling before that turbulence actually hits the fan. Now, that's quite common. I often see swirl on the noise cam pictures, either to the left or the right, depending on which way the fan's going around. Now, so there's a difference of view, if you like, between what I see on noise cam, what Owen's seen on the strings. Paul Hibbard was kind enough to suggest that, well, perhaps the strings here were showing a boundary layer effect at the duct edge. You might get something different if you put them mid-duct. At the end of the day, it's a moot discussion, because we all agree that if you want to make a cruiser, that kind of low 70s, high 60s number, it doesn't matter. The advice is straightforward and unequivocal. Don't put anything in that space, because it's going to make a noise. However, if you're a racer trying to get that F1 or F2 craft down to the magic 96, and you have to put, for structural engineering reasons, good structural engineering reasons, struts and so on closer to the fan, well, you need to aerofoil those struts, and in our view, you need to test for pre-swirl. Perhaps get an earlier craft in a clean area of duct, put some, very safely, put some structure in that simulates what you're proposing to do and see what is actually happening to the air. String tests and smoke, if you want, are brilliant for finding out what's going on. So if you are going to put struts and things close to the fan, you need to test to get it as good as you can. Flow straighteners are always a huge topic. There's every point of view between those that believe that they're a waste of time and those who believe that they're absolutely essential to straighten out the swirl of air and give you more thrust. or indeed to make your rudders work better by giving them straight air rather than swirling air. I'm agnostic on that. You can use any suitable flow straightener design you want, or none, but from a noise perspective, there's a few rules. You must use 100 mil or more gap, 4-inch gap between the fan and the straightener. The number of straighteners mustn't be the same as the number of blades. If you have the blades aligning with the straighteners, so that, for example, this blade here is just passing a straightener at the same time as that blade there is passing another straightener, as opposed to that one there is passing another straightener, you will get a series of small, noises, but they're all at the same time. So they'll add up together and give you one big noise. You're going to a synchronous noise. So make sure that the blade and the flow straightener alignment is not directly coupled. Normally, most people put in, let's say, one more straightener than there are blades, something like that. The flow straighteners have got to be the correct airfoil design. There's no point putting in flow straighteners that are the wrong shape, or indeed have got pointing in totally the wrong direction. All you're doing is creating a stalled wing as the air goes over it, a massive stall wing, great source of noise. Again, your Bible here must be mud trails. The Medway and Mersey estuaries are brilliant. Every time you go out in those, you get a complete history of where your air is going back your duct in the mud trails. If you haven't got good Medway mud, well, string tests are something that you might try. And that basically you need to understand what your air is actually doing, not what theory is, what's it actually doing in your craft. I was asked about were there any distance issues between the flow straighteners or stators and the rudders. The answer is no. They can be as close or as far away as you like. Just make an observation that my 1969 craft had about a 5-foot gap between the thrust units, which were mounted amidships on the craft, on the sides of the craft, and the rudders, which are about 4 or 5 feet back at the back of the craft. That's hopeless as a piece of design. The rudders have got no air going over them really until you pick up any forward speed. And you really want the rudders at the back of the duct, as they normally are these days. But there's no issue about the gap there. The choice of fan is a big discussion point, and everybody looks at my sickle fan and says something along the lines of, "Oh, that's sexy. I want one of those. That's going to make me a quiet hovercraft." Well, maybe. It's not necessarily the be all and end all. For a start, if that's the only change you make to your craft will not be quieter, because the other dozen or so fixes that you must need, as you will have seen in this talk, haven't been done. Just fixing one source of noise won't make any difference. You've got to fix the whole lot. So is sickle the essential fan? For an integrated craft, I'd argue probably yes, but only probably. The key point is that the splitter on an integrated craft makes the noise reduction more challenging. There's always going to be some noise, however good the splitter is. And it makes the whole design more challenging. What a sickle fan does by design is it reduces the higher fan harmonic noise, the higher harmonic frequencies, the ones that will sound shrill, high-pitched and annoy the dBA meter. The sickle does reduce those because of the way the blade is distributing the noise pressure. So the sickle can compensate, in effect, for the inevitable noise from the splitter. But for a twin-engine craft, I don't think it's necessary. It might be an advantage in making it even quieter, but it's not necessary. I mean, John Gifford is demonstrating that his 7W fan, which is a non-sickle fan, it's a straight edge fan, is achieving below 72 dBA. The key is its wide chord, because the key to low tip speed, and low tip speed is really what we're trying to achieve here, is either that the blade is wider and therefore can do more load, if you like, pull more load, or that you put more blades in. Now, putting more blades in is self-destructive, because if you put in a large number of blades, you'll get a higher frequency. That will produce a noise which is inherently higher up the frequency scale and will annoy the human ear and therefore the dBA meter even more. So wide chord is the way forward. The other point to make is that all three of these Q craft that have been built so far, mine and John's, are operating within the manufacturer's recommended tip speed. In other words, the tip speed limit, I think for my 1W is something like 83 meters per second. I'm below that. The manufacturer recommendation for the 7W is rather higher. So John is has a bigger safety margin, if you like, on that. Now, the key point to make is that throughout history, we've been using multi-ring and similar fans for 50 years now, and we've almost always used them well above the manufacturer's recommended tip speed. Now, to prove to ourselves that that's safe, the Hover Club has for years physically tested new blades as they've come out, and has subjected them on a test rig to high centrifugal loads, and literally pulled them to destruction to convince itself that these blades are safe. But we also have now 50 years of experience of doing everything with these blades, putting all the sort of loads into them as we spin craft around corners, etc., and convincing ourselves from sheer experience that they are actually safe at speeds above the manufacturer's recommendations. The fact, therefore, that I'm saying that for noise reasons, I want to keep using these fans within the manufacturer's recommendations means that we're actually operating on an even higher safety margin, because we've got all that margin that years of use have shown us is safe to go into. So by sticking to that low tip speed, it's making it quieter, but we're also staying within the manufacturer's margins, and therefore giving ourselves the extra comfort, if you like, of knowing that racing experience and so on shows we could go much higher. Now, a load of other questions came up, and I've kind of pulled them all together in one miscellaneous slide here. A lot of people say to me, oh, I'm going to put a superb noise insulating cover on my engine. And my advice would be, don't bother. I put a temporary cover over Q1's engine, 2 inches of acoustic foam, lots of chipboard, thick chipboard, and so on. I mean, the cover was so constrictive that you couldn't run the engine for more than a few minutes because it got too hot and it was seized. But all the tests, noise cam and dBA meter, said it didn't make any difference. The noise on particularly the Briggs and Stratton engines and similar is basically coming from the exhaust and the air intake. It's not coming from the engine body, unless you've got a duff bearing, as we've seen in the earlier presentation. If you've got a bearing about to fail, then that might be noisy, but that's a different thing. People ask about the mesh fan guard that we put on all craft for safety reasons. I've never found it to be a noise problem. It's a 2-inch mesh. It's quite small wire. It's far enough away from the fan that any little vortices that form behind that mesh have dissipated by the time they hit the fan, so it's not an issue. Howard brought up the issue of wing fences, and is that an alternative method for stopping the splitter crossflow or spanwise flow that I described? It could be. It's not something I've tested. You've still got to address the issue of curving the blade, the splitter plate, to allow for the swirl. But anybody that wants to have a play with that, there's plenty of stuff on Wikipedia, for example, on wing fences used on aircraft wings to stop spanwise flow. Another idea that came up from Alf was, what about putting what I've called here a ring at the fan tip to stop the blade flutter and to stop tip noise. We haven't tried that. Most of the fans that I've seen that offer this feature are pre-molded smaller fans used, for example, for cooling fans on cars, and they're really rather, they're not the size that we need. I'd also observed that most of them come with, well, the blades are obviously preset to a particular pitch, so we can't do our usual trick of adjusting and tweaking the pitch to fine-tune the engine fan ratios. So that's not been tried. There are also, Sean sent me a picture of a larger ring fan tip solution. And it would be quite an interesting engineering challenge to design the duct that accommodated this ring going round efficiently. Not impossible, but quite a challenge. Nose cones were brought up again. I've never seen any noise associated with the nose or with the center of the fan hub. And I've never felt the need to put a nose cone on purely from a noise reduction perspective. Owen also contributed that he'd tried a nose cone on his rear drive, one of his rear drive craft, and that had shown that actually the thrust went down. He took it off again and the thrust went back up. So he concluded first, certainly his front, his rear drive craft, which have very clean air intakes in the front, the nose cone or spinner didn't offer very much. I've mentioned this before, but there are craft out there that in an attempt to absorb more power in a given size, often quite small fan, will put in massive numbers of blades. I've seen 16, even 20 blades. Not a good solution. Essentially, particularly, that is making the fan rotation frequency, blade passing frequency, extremely high. It means the harmonics of that will be higher. Still, it's going to sound like a jet engine. That's going to annoy the human ear. High frequencies annoy the human ear, and if it annoys the human ear, it annoys the dBA meter. So it's not a good recipe for a low dBA craft. Okay, well, thank you for watching. These two talks together are part of a TechTalk series. They're going out during the COVID-19 disruption. And you'll find them on the TechTalks page at the address that's there. If anybody's got any questions, wants to raise any observations, wants to contact us at all, if you go to that page, you'll find email links and so on for appropriate advice. Thanks very much.